Hello and welcome back to another round of chemistry on the channel, where today we'll be doing our very first Grignard reaction. Well, not my first one, but maybe yours. The Grignard reaction is probably one of the most known metal organic reactions. It was first discovered by this guy, Victor Grignard, and essentially what it does is insert magnesium into a carbon-halogen bond, which creates a carbon nucleophile. This is an extremely useful building block in organic chemistry. So useful in fact that he got a Nobel Prize for his discovery, and even more than 100 years later it's still widely utilized. It's also most likely the first metal organic reaction you will do as an undergrad, and it sort of has a reputation for not working, but if you put a bit of effort in, it shouldn't cause any problems. What we'll be baking today is triphenylmethanol, which is basically just chunky methanol, and I will need that in an upcoming video where I'll be making tetraphenylmethane. It's also the perfect opportunity for me to finally use up some ethyl benzoate which I made like 3 years ago that has just been sitting around. We will of course need some other stuff as well. Diethyl ether as a solvent, magnesium turnings and bromobenzene for the Grignard reagent itself, and the aforementioned 3-year-old ethyl benzoate. Those are all the reagents required for the synthesis itself, but we'll also need some metallic sodium to dry and clean the ether before we can use it. This cleaning step is imperative for the success of the reaction, and that is because the Grignard reagent is an incredibly strong base. What we'll be preparing today is phenylmagnesium bromide, which you could view as a benzene anion and a magnesium bromide cation. The conjugate acid of this anion would be benzene, which has a pKa of around 40. For comparison, water has a pKa of about 16, so it's 24 orders of magnitude more acidic than benzene. This of course means that the Grignard reagent will very gladly accept any mildly acidic protons, like in water, alcohols or whatever else you might find as impurities, which will destroy the reagent and in turn ravage our yield. So we want to prevent this as much as possible. By refluxing the ether over sodium, all of the impurities will be converted into salts, and when we distill the ether afterwards, those will remain in the distilling flask. This is the setup I have built for this distillation. A condenser with a drying tube at the top, then an addition funnel where we'll be collecting the dry ether, and a boiling flask at the bottom. I will need roughly 250 milliliters of ether for this preparation, and a few small chunks of sodium are more than enough for drying. I also add a few flakes of benzophenone, which serves as an indicator and will turn blue once the ether is dry. So let's close everything up and start the reflux. Now that the ether is purified, we can start with the actual Grignard reaction. All of the glassware for this step has been pre-dried in an oven to remove traces of moisture, and to keep any water out during the reaction, a drying tube has been placed on the condenser. The oxygen in the air will also slowly destroy the reagent, but since there's always a blanket of ether vapor above the reagent and we're using it right away, it's not that big of a deal and we don't have to worry about it here. Mixing will be done by my trusted KPG stirrer, since Grignards have a tendency to turn into rocks as they progress, and with a mechanical stirrer it's more like rock slurry, which is much better to work with. 6.6 grams of magnesium turnings are now added to the flask, and these are then submerged in a small amount of dry ether. An addition funnel is then placed on the side neck and filled with 40.83 grams of bromobenzene, which is the alkyl halide we're using. Now we can begin with the hardest part of the Grignard reaction, which is getting it to start in the first place. I add a small amount of bromobenzene into the ether, and the indication for the reaction start is that the solution gets noticeably warm and cloudy. Unfortunately, that doesn't happen, even after a few minutes of waiting, so I'll need to assist a little bit. One common thing to do here is add a small crystal of iodine. This will etch the oxide layer on the magnesium surface and expose fresh metal which is able to react with the bromobenzene. A few minutes of waiting later, nothing has changed. So we'll need to do a little more convincing by additionally heating the mixture with a heat gun. If you now look closely at the flask, you can see that the reaction mixture starts becoming more opaque from this point forward. So this is our sign that the reaction has begun. Now we need to start adding new bromobenzene fairly quickly, because if the reagent in the flask is ever depleted, the reaction will die, and we would have to do this whole part again, so let's try to avoid that. The bromobenzene in the funnel is first diluted with some more ether, and now we want to add the solution at a rate that sustains a light boiling of the ether in the flask. This can now run by itself, so let's go over the mechanism. In this step of the reaction, the magnesium transfers an electron to the bromobenzene, forming a radical anion. This significantly weakens the carbon-bromine bond, so the bromide ion is kicked off, leading to the formation of a carbon-centered radical. The magnesium then forms a bond with the carbon radical, and the bromide comes in from behind to form the Grignard reagent. There's also a side reaction here where those phenyl radicals can combine to form biphenyl, which will be important later, so keep that in mind. What this whole sequence does is transform the partially positive carbon in our bromobenzene into a partially negative carbon. This type of transformation is known as Umpolung, which means that it reverses the polarity of a functional group and therefore also reverses its reactivity. This is a very important technique, especially in retrosynthesis, and can be very useful for many different transformations. Now let's finish up making the reagent, and then we'll make use of our nucleophile in the next step. The formation of the Grignard reagent should now be completed. At least I have to assume that, because the only real way to tell would be by NMR or titration. Whereas I can't do the first one and I don't want to do the second one. The main indicator I have is that most of the magnesium has disappeared, except for a few small flakes, so it must have gone somewhere, and it's very unlikely that it just disappeared into thin air. The solution has also taken on a very dark brown color, but no need for concern, that's expected to happen. At least it's not yellow. With the first step of the reaction completed, we can now move on to making a new carbon-carbon bond by reacting our phenylmagnesium bromide with ethyl benzoate. In the last step, we performed an Umpolung reaction on bromobenzene, so this carbon is now a nucleophile, and we can use that to attack the electrophilic carbonyl position in the ester group of ethyl benzoate. An ethoxide ion is then kicked out as a leaving group, and we will form this intermediate, which you might recognize as benzophenone. This intermediate also possesses a carbonyl group in the form of a ketone, so it can react with another equivalent of phenylmagnesium bromide, and then form the alkoxide of triphenylmethanol, which is the final step of the reaction. Isolating the benzophenone intermediate is not possible with this reaction setup, because the ketone will react faster than the ester and is therefore favored by the Grignard reagent. However, there are tricks to making ketones with a Grignard reagent by, for example, using Weinreb amides, which trap the transition state in a chelate complex and therefore prevent further reaction. But we're not doing any of that fancy stuff, we're just using an ester. So I add all of my 16.7 grams of ethyl benzoate into the addition funnel and then use a bit of ether to wash out the flask. The ester is then slowly added to the Grignard solution. This part is much less exothermic than the formation of the Grignard reagent itself, so it doesn't have to be added as slow, but I still take it off heat just to be safe. The reaction mix also seems to take on a kind of cherry red color, but that quickly fades away. The solution is now refluxed for 2 hours to fully complete the reaction. You can probably spot when that will be the case. The reaction is now complete and you can see that the reaction mixture has turned into a very thick paste. It's very similar to bread dough in consistency, and the main ingredients are a bunch of different salts containing magnesium and bromide ions, the alkoxides of triphenylmethanol and ethanol, and the ether we used. Most of these salts are strongly alkaline, so we have to do an acidic workup to dissolve all of the junk and separate the triphenylmethanol. This is the easiest part of the synthesis, so there's no way anything will go wrong here. Neutralizing a rock which is mainly made out of alkali is a very exothermic process. So first I'm gonna add a bunch of ice to help cool the reaction, and as an additional precautionary measure, I also reattach the condenser to catch any ether that might start boiling. The boiling point of diethyl ether is 36 degrees, so it doesn't take a lot. With everything set up, I now start adding 2 molar hydrochloric acid through the condenser. As expected, the ether starts boiling pretty much immediately. You can see this especially well in the joints, because they become transparent as the gap is filled with a thin film of condensing ether. After quenching the solution, there is still a bunch of white solid left over. This shouldn't be magnesium chloride or bromide, because they are both highly soluble in water, and it's definitely not any hydroxide when the solution has a pH of 2. So it's probably triphenylmethanol. With a bit more ether and a tiny bit of mechanical assistance, I get most of it to dissolve except for a little bit of crust, but that's not too bad, I can just clean that up later. The solution is now transferred into a large separatory funnel, and the aqueous phase is drained into a beaker. I collect the organic phase in a separate flask, and the aqueous phase is poured back into the funnel and extracted twice with diethyl ether. There shouldn't be a lot of triphenylmethanol in this phase, since it's basically insoluble in water, especially with all of the salt dissolved, but it's better to be safe than to be sorry. The combined organic phase is then washed once with water and dried with a few scoops of anhydrous magnesium sulfate. I let this sit for about an hour so the drying agent can do its job, and now I would like to filter this solution into a smaller flask. But there's a little bit too much ether in there for that, so I do a little tactical distillation and remove about 100 ml of solvent. Usually you shouldn't heat a solution with a drying agent, because it can release the water it absorbed back into solution, which kind of negates the drying step. But ether has such a low boiling point that it shouldn't cause any problems. With the reduced volume, I can now filter the solution through a cotton plug into a 250 ml flask. The drying agent is washed with a small amount of ether to make sure I get all of the product out, and now the flask is put back onto the distillation setup so I can fully remove the solvent. Once no more distillate is coming over, I pull a strong vacuum on the flask for a couple of minutes to remove any solvent that is still left. But we can already see there's a large amount of solid in the flask, which has formed a very interesting pattern during crystallization. There's a bunch of yellow gunk on the outside and some nice white crystals on the inside, kind of like a reverse egg. But when I shake the flask and mix everything, it just turns into a light brown powder. Actually, you wouldn't call this brown, this is off-white, which I guess sounds a little nicer and is basically just a way to professionally gaslight yourself into believing you actually have lab skills. We definitely have to purify this, and the standard way to do that is recrystallization from ethanol. I add about 100 ml of absolute ethanol to the flask, and then heat the solution to reflux. Everything dissolves cleanly in the hot ethanol, and now we can let it cool down to obtain some nice and clean crystals. Those are definitely not nice crystals. No need to panic, I'll just remove the ethanol under vacuum and then redissolve it in some ether and try to do another aqueous workup. Then just quickly dry the extract and remove the solvent again, and we can attempt another recrystallization. Second time's the charm, you know? Oh no. Oh no. This is the part where I started panicking a little bit, because I had no clue why this was happening. A bunch of procedures use this exact method without issues, but of course as soon as I do it, it doesn't work. So now I have to fix this somehow, and this is what I came up with. During the acidic workup I was using HCl, so maybe the triphenylmethanol had undergone a nucleophilic substitution, which has replaced this alcohol with a chloride. The idea isn't that far-fetched, right? Under acidic conditions we have a good leaving group in the form of H2O, and the resulting carbocation is a triphenylmethyl cation, which is super stable. This would leave us with trityl chloride as an impurity, which in the following recrystallization in ethanol could form triphenylmethyl ethyl ether, which could potentially do some weird eutecticum crap causing the yellow slime to form. Those are a lot of woulds and coulds, and in retrospect, this idea isn't very good. But I was panicking, okay? When you're panicking, you don't have good ideas. Anyway, we're not in the retrospect yet, so enjoy the next few minutes with a grain of salt and just laugh about me being an idiot. So, what is the plan now? Well, assuming that the only impurities we have are trityl ethyl ether and trityl chloride, we can just work our way back through this reaction scheme towards triphenylmethanol. This means the first thing on our list is cleaving this ether bond here with a strong halogen acid. My choice fell on hydrochloric acid, which is a fairly unusual pick for this type of reaction. The way ether cleavage works is an initial protonation of the ether oxygen to create a good leaving group, followed by a nucleophilic substitution reaction, which can proceed either via SN1 or SN2 mechanism. SN1 requires a stabilized carbocation and SN2 favorable sterics, so the usual SN rules. The nucleophile, which I have marked as X here, is the conjugate base of the acid that is used. For this reason you want an acid that combines both high acid strength and nucleophilicity, which is usually HI or HBr. The problem with HCl is that it's the worst candidate for both requirements. It's the weakest acid of the bunch, and chloride is also a poor nucleophile, so most acids won't even react with it. But in this case, if I cook the reaction really hard, I should be able to force it to the SN1 path, which proceeds through the incredibly stable trityl cation, and then the nucleophile isn't as important. So with that said, I'm just gonna take the yellow crap and reflux it with concentrated hydrochloric acid for a couple of hours. After that, the acid is decanted, and I dissolve the residue in some ether and perform an aqueous workup to get rid of any acid or side products in the reaction. After that, the solvent is removed, and the resultant solid is even more yellow than what we started with. So, is that an improvement? I'm not sure, but hopefully it gets better after the next step, because now we have to convert all of the trityl chloride in here back into triphenylmethanol. Again, this should be fairly easy to do through nucleophilic substitution. only this time our nucleophile will be a hydroxide ion, which is supplied by sodium hydroxide. I make a fairly concentrated solution with a large excess of hydroxide, and I add all of that to the yellow solid and heat it to reflux. You may have noticed that throughout this part I didn't really pay attention to stoichiometry. This is in one part because it doesn't really matter as long as we have a bunch of excess reagent in the flask, and also because I was quite annoyed at this point that nothing seemed to work, and got progressively worse as I proceeded. After a few hours of refluxing, I let the solution cool down and filtered it to obtain the product. And all of this should in theory be triphenylmethanol, but well, you don't need any fancy characterization to tell it's not pure. I mean, it's at least solid now, but it looks much worse than before. And it also has like a weird slimy texture to it. So yeah, that workup was an absolute disaster. But then a brilliant thought struck my mind. What if I just changed the solvent for the recrystallization? An ingenious idea that I could have come up with before doing all the crap with the acid, but nonetheless a glimmer of hope. Triphenylmethanol is moderately soluble in toluene, but it's almost insoluble in hexane. So I took all of the slimy crystals from before and dissolved them in hot toluene. And after it starts refluxing, I begin adding hexane to the solution as an anti-solvent. Eventually, the solution starts turning cloudy, which is a sign that we're reaching the point of saturation. So now all I can do is place it in the freezer and hope that this time it actually crystallizes. Look at that! Beautiful crystals on the side of the flask. We have finally escaped the slime, and after filtration, the product looks amazing. Unfortunately, the color isn't quite right. The pure product is supposed to be colorless, and ours is more of a brownish yellow. I ran another recrystallization to hopefully get some of the color out, and it worked pretty well, although it's still not white. I could have tried a hot filtration with activated carbon, but I checked the melting point and it's spot on, so I don't really care. After all this effort, I have managed to isolate a full 18.77 grams of product, which is a 68% yield. That's not terrible considering all of the crap I did, but still I feel like I could have done better. I mean, this whole thing took like a week, and after all that, the product isn't even the right color. You know what? I'm doing this again, but this time I'm doing it well. So it's time to bring out a piece of equipment I recently acquired. This is a Schlenk manifold, which is essential for conducting reactions under inert conditions. And what could possibly be a better way to inaugurate this piece than doing an overkill Grignard reaction to please my own ego? For the second run, I will put much larger emphasis on the purification of our starting materials. After all, there is little use in switching to inert conditions when your chemicals are dirty. Although that wording is very nitpicky, I'm mostly referring to dissolved oxygen and water, which nonetheless is very destructive for this type of chemistry. For the most part, you've already seen everything I'm about to do here, so I will leave this part mostly uncommented. I have only changed two of the reagents, so let's go over that quickly. First of all, I'm using methyl benzoate instead of ethyl benzoate for the simple reason that it's cheaper. And second, I changed the solvent to THF because its boiling point is higher, which makes it easier to work with under vacuum. But overall, the reaction stays the same, except that we now have a different leaving group. With that said, we can now start the second run, so tuck in your seatbelts and enjoy the ride.
There's a place where we can go tonight. The rhythm will
And with this beautiful shot, we have completed the second synthesis. This whole sequence, which for you lasted about 6 minutes, took me 4 days. Although 2 of those were spent waiting for the reagents to dry, so count them in or not. The crude product in this run already looks super amazing, and just by visually comparing with the crude from the first run, you should be able to tell which one worked better. The mass of our crude product is 22.5 grams, which is a 98% yield. Holy moly! Of course, it's not actually 98% because the melting point is way off, so we will have to recrystallize it, but still, that is very impressive. I'm recrystallizing this the same way as before, except that I'm using petrol ether instead of hexane, because I ran out of hexane, but it's basically the same thing, so it doesn't matter too much. I'm gonna let this run in the background, so in the meantime I wanna go over 2 things from this run. First thing is the activation method for the magnesium. The way I've done this so far is like you've seen at the beginning, where I dissolve the iodine in ether and then stir it for a couple of minutes and add the aryl halide. This usually works, but it really isn't the best. It takes time and sometimes it's a bit stubborn and doesn't really want to go, basically what you've seen in the first run. But while researching for this video, I have discovered another method where you heat the magnesium with the iodine crystal when it's dry and basically sublime it onto the metal surface. And let me tell you, I have never started a Grignard reaction this fast, so I'm definitely gonna use this method in the future. And the second thing is regarding the purification of the reagents. This was my first time using molecular sieves to dry something, and I massively underestimated just how much liquid would get trapped by the sieves. Originally, I calculated this preparation with 12.5 milliliters of ester, and I anticipated that I wouldn't be able to get all of it from the flask, so I included an additional 2 milliliter buffer just in case, but as it turns out, that was nowhere near enough, and I really had to struggle to even get 11 milliliters of the reagent. It also didn't help that I probably used way too many sieves, so that is something to keep in mind for the next time. But overall, I had a lot of fun during the second run. A lot more than during the first one. The recrystallization seems to be done, so to get a few more crystals I leave this in the freezer overnight, and now we can filter it and then take a look at the final product from this run. And damn, this is what triphenylmethanol is supposed to look like. A crystalline, colorless solid, and the melting point is absolutely spot on. In fact, the difference to the first run is so big, you can see a clear line in the storage bottle between the 2 products. Of course, this isn't just because of the Schlenk line, you can also get a perfectly good product without this much effort, if you just don't screw it up like me, but it's still satisfying to see the improvement. In an effort to get some more product from the mother liquor, I removed most of the solvent and got a bunch more crystals out. These are very impure. I didn't bother getting an accurate melting point because it's way under what it's supposed to be anyway, but with a bit of love and a few more recrystallizations, I managed to get an additional 2 fractions out of this. They're not quite as pure as the main batch, but since I'm gonna use them in another reaction anyway, I might as well include them in the yield, which brings us to a combined total of 20.58 grams of product and a whopping 90% yield, which I feel like is the perfect conclusion to this roller coaster of a video. That was definitely an experience, so to everyone still watching, thank you for staying with me until the end of this behemoth, and of course a huge thank you to my amazing patrons for supporting me even though I don't upload too much. I really appreciate it. In the next video, we'll be continuing the synthesis and making tetraphenylmethane. So until then, I wish you all a great time and also probably Merry Christmas and Happy New Year, so stay safe and see you soon.